Okay, so here's another example. Again, with simple torque where we just are, well, pure torque, and we aren't indeterminate. It's just like a cake problem. We have to find internal torques. We can then find shear stress, and then we can find rotation. So I have a solid steel shaft of variable diameter is subjected to the torques shown. The diameter of the shafts in 1 and 3 is 50 millimeters. The diameter of the shaft in segment 2 is 80 millimeters. The bearings allow for smooth rotation, determine the maximum shear stress, determine the rotation of angle of pulley D with respect to A. So when we do our rotation, we're going to do it with respect to A. Whoops, with respect to A. Okay? So the first thing we have to do is find our internal resisting torque, calculate the shear stress, and then calculate the rotation. When I look at these segments, when I look at segment A, B, and CD, so when I look at A, B, and CD, we know it's all solid. We know that all of it has the same material. So the outer diameter is 50 millimeters. So the outer radius is 25 millimeters. And again, 0.025 meters. 1, 2, 3. Okay, I need everything in, I don't know why this is not focusing so well tonight. Okay, I need everything in meters and in newtons. I also know that G is 80 gigapascals, which is 10 to the 9th. 10 to the 9th, and a pascal is a newton per meter squared, so my units are acceptable. And if it's solid, we have pi over 2 c to the 4th. Okay, and remember, maximum on the out, c is just the radius. When I look here at BC, it is also solid. It has an outer of 80 millimeters. So our radius is going to be 40 millimeters, which is 0.04 meters. Again, this equals c. So we have pi over 2, c outer to the 4th. That's j. And this is j. So we kind of have everything going on. We do have these lengths. So I could put my length of 0.7 meters. I could put my length of 1.8 meters. And I think we have everything that's been given in terms of shaft 1 and 3, and then shaft 2. Now I just need to find internal torques. So if I'm coming from the right to the left and I cut, I have an applied 500 Newton meters. I'm going to assume my internal is positive. Okay, so I'm in the direction of going away from that cut section, twisting into the page. So we are going to sum our torques. We're going to call that positive equals 0. So as I'm looking here, I have a positive. So this internal torque we have is torque from D to C. So I have a torque from D to C. Okay, positive, positive, positive. That's also showing positive if I'm going from left to right. So plus 500 Newton meters. So the torque from D to C is a negative 500 Newton meters. So I could go ahead and put that over here. We are at negative 500 and my units are a Newton meter. Okay. Now I need to come across and cut it here. So I'm going to come across, cut it, and cover up everything to the left. Again, I have 500 going back. I have 2800 going back. That means in order to be, if I'm looking at this, okay, as positive. So assuming positive, it would be going back, going back, going back. It's got to be negative coming back towards me to balance this out. So I'm going to have an internal torque here of negative 8, 9, 10, 11, 12, 13, 3,300. So I can draw that kind of like right here. Negative 3,300. I can either continue to go across and have negative 500, negative 2,800, positive 4,500. And I'm going to find that I have an internal value of 1,200 in order to keep this system in check. Or instead of doing all that adding, I'm going to come from the other direction. So if I have the 1200 being applied, right hand rule tells me coming towards me is positive. I'm going to have the torque from A to C if I'm summing. So I have torque A to C, positive, 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 minus 1200 equals 0. So torque AC equals 1200. Okay. If I'm going to use, when I sum my torques, I have to use the same rule all the way down that shaft. So I have TAC, negative 1200. And I can tell that I end up getting a positive 1200, which makes sense. They are equal and opposite. So here is my torque diagram. So how do I calculate stress? Well, I know that stress is T rho over J. And if I want maximum, it's TC over J, and C is my radius. Okay? So if I'm looking at this segment 1, I have a torque of 1200 Newton meters, positive. I have C. C is my radius, that outer radius. J is pi over 2, outer radius to the 4th. So if I'm looking at this section, shear stress equals, I have 1200 Newton meters times that outer radius is 0.025 meters divided by J, which is pi over 2, 0.025 to the 4th. So let's just kind of work this out here. 1200 times 0.025 times 2 divided by pi divided by 0.025, 25, 25, 25, and I get this really ginormous number. But this, we have to remember, is in Newton per meter squared because that's the units I've been working in. So I'm going to go 1, 2, 3, 4, 5, 6. So I have 48.89 kilomegapascals. Okay, 48.89 megapascals. And if I want to draw that on here, then for my shear stress, it's positive, and we are at 48.89. Okay, so now I can find the shear stress of this middle part. We have a negative 3,300. Okay, my outer radius, 0.04 meters, divided by pi over 2, 0.04 to the 4th. So I'm going to do the same thing. We have 3,300, 3,300, which is negative, times 0.04, times 2 divided by pi, divided by 0.04, 0.04, 0.04, 0.04, and I get this very large number. And again, this is in newtons and meters because I've got everything consistently in Newton meters. So we can call that kilomega, minus 32.83 mega, minus 32, minus 32.83. So if we look, even though it has a much larger torque, 3,300 versus 1,200, our shear stress is actually smaller because we have that much larger diameter, okay? And our shear stress is a function of our geometry. We have that much larger diameter, so it's able to reduce that stress. Now we can do the same thing over here, and we're going to have a negative 500, and we're going to go back to the properties for C to D. So times 0.025 divided by pi times 2 divided by 0.025, and I get negative 20,000.371, blah, blah, blah. Again, this is in newtons and meters because I keep all of my information in newtons and meters. Kilomega, negative 20.37. So kind of come up here. negative 20.37 Newton per meter squared shear stress. So we had an internal torque of 1200, an internal torque of negative 3300, and an internal torque of negative 500. Internal stress of positive 48.89, internal stress of negative 32.83, internal stress of negative 20.37. So the maximum overall shear stress that we have for our system is 48.9 megapascals. And now we just go back through and find our angle of twist. And what is our equation for angle of twist? The units are going to be in radians. TL over JG. Okay, so I'm going to do the exact same exercise. I'm going to plug in my T. It's either going to be positive or negative. I'm going to plug in my length given. J, same thing we used for shear stress. G is material properties. And I've got to make sure that I'm using correct units. Okay, I have to make sure. And what I find is that my phi for this section is 0.017112 radians, and that's a positive value. I found that my phi for this section, okay, my phi for this middle section is a negative phi because I have that negative internal torque and I have that negative internal shear stress. So we are going to have a negative rotation, and I get negative 0.018464. When I look at this segment, I'm also going to have negative resisting torque, negative shear stress, negative rotation, negative 0.007130 radians. Okay, so what does my diagram look like? This time I want it with respect to A. So A is going to be considered 0, and I have a positive rotation, so we're going to go up to 0.017112. Okay, let's type that in. 0.017112 minus, okay, the rotation, good grief. Here we go. Minus the rotation of segment BC. So minus 0.018464, and I get negative 0.01352. So I've crossed over, and I didn't draw that very well because I didn't pull out my straight edge. So I have negative 0.001352. And then I'm going to add to that some more negative rotation, minus 0.007130, and I go down even farther, negative 0.008482. So what does this mean? Okay, what does this mean? It means our total angle of twist is in the negative direction. So if this is it's twisting towards the back, and it is 0.008482 radians. And what does that mean in terms of degrees? Well, I can multiply that times, if this is radians, times 180 divided by pi, and I get it's roughly 0.48 degrees. Okay, that to me is easier to understand than radians. It also means that somewhere in this part of the shaft, I've gone from a positive rotation, okay, where I'm rotating to the back, to a negative rotation where it's just an opposite. I could actually, if I wanted to, I could calculate back that distance to where we had 0 rotation. That as we were switching from